Hey everyone! Today we're doing a deep dive into a really fascinating research paper. It proposes something pretty radical. What if you could write a single, unified mathematical formula? A recipe, really, for perfectly stable and predictable game physics. You know, physics that just works. No more random explosions. Let's break down exactly how they do it. So here's our game plan. We're going to start with a problem that I guarantee every single one of you has seen. Then we'll unpack the paper's incredibly elegant solution piece by piece. We'll look at the big picture, the nitty-gritty math, and even the formal proofs that guarantee this thing is rock solid. And we'll wrap up with why this whole approach is such a game changer.
All right, let's kick things off with a scene that is probably way too familiar to anyone who's ever played a video game with a physics engine.
Oh, you know what I'm talking about. You spend 5 minutes carefully stacking some boxes, just so, and then suddenly they start jittering like they've had way too much coffee. Or maybe you gently nudge your car against a wall, and for some reason it decides to launch itself into the stratosphere. That chaos, it's a classic symptom of a physics engine that's struggling. Tiny little errors in calculation are building up, frame after frame after frame, until, boom, the whole thing just breaks. Well, that chaos is exactly what this paper, a unified operator proposition for level 2 manifold physics, is designed to eliminate. Instead of patching things up with hacks and weird tweaks, it lays out a single, unified blueprint for a physics engine built from the ground up on a solid mathematical foundation. See, to be considered truly modern and reliable, an engine has to hit 3 main goals. First, it has to be stable. A stack of boxes should just sit there, no jitters. Second, it's got to be deterministic. This is huge for developers because it means replays are always perfect and bugs are repeatable. And maybe most importantly, it has to be bounded. This means energy can't just magically appear out of thin air to cause those ridiculous explosions. And this, right here, is the core idea that changes everything. Instead of thinking about a physics update as a dozen separate, messy steps that might fight with each other, this paper frames the whole thing as one single mathematical function, an operator. You feed it the current state of the game world, you turn the mathematical crank, and out pops the state for the very next frame. It's a completely holistic way of looking at the problem. So how do you actually build this big unified operator? What's going on inside the machine? Well, let's pop the hood and take a look.
It's an 8-stage assembly line. First, we integrate. That's just a fancy way of saying we move everything according to its current speed. Then we use a grid to quickly figure out which objects are even close to each other. From there, we list all the potential collision pairs, and then we do what's called a narrowphase check to find the exact points of contact. Now, here's where the magic really starts. We update a cache that remembers old collisions, use that memory to warm start the system with the forces from the last frame, then we solve for any new forces, and finally, we put anything that's not moving to sleep to save processing power.
That cache we just mentioned, that is the absolute secret sauce. The paper calls it a level 2 manifold cache, which, sounds complicated, but you can just think of it as a kind of collision muscle memory. It remembers how hard objects were pushing on each other in the last frame. By applying those old forces as a starting guess for this frame, things like a stack of boxes will settle down almost instantly, instead of doing that awful jittery dance for a few seconds.
Okay, let's zoom in on the most critical part of this whole pipeline, stage 7, the solver. This is the beating heart of the engine. It's where all the real number crunching happens to figure out how objects should react to each other.
The main currency that the solver deals with is something called an impulse, and it's represented by the Greek letter lambda. The best way to think of it is as an instantaneous kick. When two objects are about to pass through each other, the solver's entire job is to calculate the perfect-sized kick needed to stop them. And this is the formula it uses to do it. Now, I know it looks a little scary. Math formulas can be intimidating, but stick with me, because what this equation is describing is actually super physical and really intuitive. Let's break it down piece by piece. So what is this actually saying? Well, that first part, the negative Vn, that's just the speed that the two objects are smashing into each other. It's the problem we need to solve. The plus b is a little bias, a gentle nudge to correct for any tiny overlap that might have already happened. And then we divide the whole thing by dn, which is the effective mass. That just tells the solver how hard it needs to kick to get the job done, right? You need a much bigger kick to stop a bowling ball than you do a ping pong ball.
Okay, so we have our pipeline and we have our solver. But how can we be absolutely 100% sure that it won't explode? Well, unlike older engines that kind of rely on careful tuning and a bit of luck, this paper gives us a formal mathematical proof.
The goal of the proof is to show that our entire 8-stage operator is what's known as a contraction. In mathematics, a contraction is a special kind of function that is guaranteed to always bring things closer together. If our physics step is a contraction, it means the simulation is always calming down. It's a mathematical promise that things won't spiral into chaos. The proof is built out of a couple of simple, common-sense building blocks called lemmas. And the first one is pretty obvious. Adding damping is a contraction. Damping is literally just multiplying velocities by a number a tiny bit less than 1 each frame. Of course, that removes energy from the system and calms things down. Easy enough.
The second building block is about something called projections. All this means is snapping a value to the nearest allowed state. Think of it like putting a speed limit on an object, or making sure a contact force can only push and never pull. These are like safety rails. And crucially, these safety checks can't add new energy or create more chaos. The math term is non-expansive. They can't make things worse.
And when you put those two simple ideas together, you get the paper's final powerful conclusion. Because our entire unified operator is just a sequence of steps that are either contractions, like damping, or non-expansive, like our safety clamps, the whole thing put together is a contraction. This isn't a hunch, it's a formal proof. The system is guaranteed to be stable. It literally cannot explode.
So let's bring this all back home. We have a system that's stable and bounded. It won't explode. But what about that third critical goal we talked about way back at the beginning?
Determinism. Because our entire physics pipeline is one single, well-defined mathematical function, if you give it the same starting conditions, it will produce the exact same results every single time. For game developers, this is the holy grail. It means network replays are perfect. It means that impossible to find bug now happens every single time, so you can fix it. It means competitive games are fundamentally fair.
What this unified approach really does is it transforms game physics from this chaotic, unpredictable art form into a predictable science. It takes all the wild emergent behavior of countless objects bouncing around and tames it with the rigorous, beautiful structure of mathematics. It lets us create virtual worlds that aren't just believable, but are provably, reliably stable. It's pretty amazing stuff.